introduction. First of all, thank you, Erwan and Evgeny, for the invitation, for giving me the opportunity to give this talk. So I want to talk about convergence of stochastic optimization algorithm in a derivative-free context. And I have to say that this title was inspired by a discussion with Sean Main. So Sean Main is a specialist of Markov chains theory and stochastic control. And when looking at some results, I will present in the second part of the talk, so some convergence result of stochastic algorithm. He told me that in the first place, he didn't expect such a fast convergence rate. And the reason why he didn't expect served me as a motivation for the first part of this talk. As I said, so we are in a context of numerical optimization. So we want to minimize the function f of x, which is defined on r to the n, or subspace omega of r to the n. So n in this talk denotes the dimension of the search space. And we can assume that the function is noisy, which means that what we want to minimize is not just a deterministic function, but we have also xi, which is a random variable, and we want to minimize this. So typically we could imagine that the function f of xi is just a noiseless function f tilde of x, where we add, let's say, a random variable which is a Gaussian noise with variance epsilon square. Or we could also imagine a multiplicative noise, f time of x, f tilde of x times xi, where xi is positive. And typically the way we formulate then the optimization goal is we say that we want to optimize capital F of x, or minimize capital F of x, which is the expectation of f of xi, and we take the expectation over the noise here. So I was saying that we are in a derivative-free or gradient-free optimization setting, so which means that we want to minimize the function f of x or capital F of x, but we assume that we don't have access to the derivative of small f or capital F, or not the derivative also of the noisy part of the function derivative with respect to x. So this is also a scenario that we call zero-order black box optimization. So zero order means because we have to minimize without access to gradient or derivative. And black box, this is to picture that the algorithm has to be able to minimize the function without accessing any information about the problem, about the function, than a black box that he can query. So he can ask at the input of the black box, give me, for a given vector x of r to the n, the function value, f of x, or the noisy function value. So this is a very typical setting in application. So many applications are formulated as derivative-free or gradient-free optimization problems. And also this black box setting is typical for many problems. In industry, it's very common that the function that need to be minimized is really given by a black box, because the function is given by a source code, and we don't have access, or people do not have access to the source code. So they really need algorithms that are capable to minimize without looking into the black box. Right, so in my title, I said I talk about stochastic algorithm, and we can ask ourselves why stochastic algorithm. So usually we motivate stochastic algorithm for black box optimization because we say they are typically more robust to noise, and more robust also if you have outliers or non-convex problem. And this is typically a cut of it's four-dimensional function. It's a cut of a function that looks pretty noisy, a cut along one direction. And this here, the other representation here, we just look at the level set of a function. We pick up two variables and we look at the level set, which means lies of equal function value. And as you can guess here, it's a function with plenty of local optima. You actually have exponential number of local optima with respect to the dimension. All right. So I said usually we argue why stochastic algorithm, because they are more robust. But today I also will present some data about this statement, more robust to noise. So we've been recently testing robustness of different algorithms on some benchmark. So why benchmark? Because if we want to validate or if we want to test performance, theory is typically not enough. So we also need to have benchmark. And here I'm taking a benchmark set, which is called BBOP. BBOP stands for Black Box Optimization Benchmarking. So there are 24 functions. They are implemented within a COCO platform, so that you can find here. COCO stands for Comparing Continuous Optimizers. And those 24 functions, they are, on the one hand, scalable with respect to the dimension. And they are supposed to represent difficulties of real-world problems. So typically, they are convex, but also non-convex problems. So they include, in particular, multimodal function, non-separable, and ill-conditioned problems. So ill-conditioning is a very important difficulty that many real-world problems have. And those test functions try to represent, in a statistical way, all those typical properties that we are expected, or that we expect to encounter in real world. And I have a small visualization of the function. So first of all, I also have the plot here of the function. So this is 2 of the 24 functions in 2 dimensions. And the way we represent it also, this is via this level set. So we look at lines of equal function value, but here we have normalized them to be such that they are comparable. So all values are between 0 and 1. But basically, this still gives an idea of the difficulty in terms of level set. And so I said there are 24 functions, and here I display the 12 first functions. So the first one, you can guess, is pretty easy. It's just the Euclidean norm. You have to minimize the distance to the black cross. Here it's slightly modified convex quadratic. And there you start to see some difficulties, multimodal functions. Those one are unimodal, just a single optimum, all this. But you see that the sub-level set are here are non-convex. So those are the first 12 functions. I have the second half, so from F12 to F24. So you see that they present some difficulties, multimodal, also highly rugged. And I think one of those 2 correspond to this one. All right, so this is the test functions where we want to test robustness of algorithm with respect to noise, and I test deterministic versus stochastic because this is to motivate stochastic algorithm. And in terms of deterministic algorithm, I take the BFGS. Sorry about that. So first of all, I have to explain how we display performance. So this could be challenging to represent the performance on 24 functions. So we don't use table with performance on each function, but we use something which is pretty cool, which is basically present this way. So I will explain how to do that, because I guess you are not all familiar with this type of plot. So what we display, so we collect for a given function, we define some target, and we collect how long it takes to reach the target. So how long, we call this runtime, but this means how many function evaluation do I need to reach a certain target. So we collect this typically for one function, we have 51 targets, and we collect this for 24 functions, which means that overall we have 24 times 51 number of function evaluation. And those data, now we can display in an empirical cumulative distribution function. So on the x-axis, we display the number of function evaluation, we normalize by dimension, and we put a log scale. And then on the y-axis, we have therefore the fraction of problems that are solved. And this way we can display the performance of one algorithm, so one color is one algorithm, on a single graph. So we have aggregated this performance. And how do we read this? So ideally, if we have a hypothetical algorithm that can solve all 24 functions in one, all 24 problems in one function evaluation, so it's not possible, but let's think about it, how it will look like. So it will look like in one function evaluation, we would solve all problems, so this ECDF would be on the left and up go to 1. So basically, the better the algorithm, or the more problem the algorithm can solve, the higher the ECDF is, and the more to the left as well. So ideally, we want ECDF as much as possible to the left. And so here, for instance, those algorithms, we can see that the blue algorithm solves more problem, but the green algorithm can solve some problem faster, almost a factor of 10 faster in the beginning. All right, so that's the way we can represent performance in a single graph. Now, I said we want to test deterministic versus stochastic algorithm. So in terms of deterministic algorithm, I will consider the quasi-Newton algorithm. So I think many of you know quasi-Newton. So it's an algorithm. So it's deterministic algorithm. Originally, it's with derivative. So it's a gradient-based algorithm. And the way the algorithm works, so you have theta t, which is the estimate of the optimum at iteration t. So in my talk, t represents the iteration index. So t is a discrete iteration index. So theta t estimates the optimum, and the way you update theta t is by taking you take the direction which is the gradient, but you multiply the gradient by the estimate. Bt is the estimate of the inversation, and this bt is also updated, and bt is updated just with gradient update. And we know, ideally, we would like to have this Newton direction, which is inversation times gradient, but it's expensive to estimate. So there is, in quasi-Newton, we estimate this Newton in an iterative way, just with gradient update. So now I said we are in a derivative-free setting, but I'm talking about a gradient-based algorithm. So why do I do this? Because basically we can transform this algorithm into a derivative-free algorithm by just estimating the gradient by finite differences. And because BT update also involves gradient, we can just inject also the finite difference estimate. So therefore now I have a deterministic algorithm, which is pretty strong and pretty standard deterministic algorithm, and I can compare it with respect to a stochastic algorithm, which is called CMES. I will come back on this algorithm later in the presentation. All right, so I want to test robustness to noise outliers. So I consider the 24 functions that I have presented, and I just add, with a certain probability, some noise. So here I add a Cauchy noise to model more the outlier case. And just for the test I'm presenting, I just add absolute value so that I basically make function value worse than what they are really by doing this. And as I said, I do this with a certain probability. And the probability goes from 0. So 0 means I test without outlier noise on the 24 function. And I increase this probability up to 0.4. And now I display the ECDF that I have shown before for, on the one hand, BFGS, and on the one hand, CMES. And this is how it looks. So on the left, we see then the BFGS. So I picked up 10-dimensional performance. I could have picked another dimension, but this is the one I chose. So in dark blue, this is without noise. So this is the performance of BFGS without noise on the left, and performance of CMES without noise on the left, also in blue. So we basically see that BFGS is faster than the CMES algorithm for in the beginning, right? And now we see that having this noise impact the performance quite a bit. The ECDF go down. And on the other hand, for the stochastic algorithm, we see that it's almost, I mean, it's not very sensitive to having this noise, because almost all ECDF are the same. We still see some effect of the noise, right? The ECDFs are a bit different, but not too much. So this is to illustrate, or this is some data that illustrates some robustness with respect to noise outlier for stochastic algorithm. And there's a motivation. Yeah, go ahead.
Could you recall again what is the BFGS and CMA?
What are those algorithms? Okay, so BFGS is a quasi-Newton.
That's the quasi-Newton.
Yes, okay. Quasi-Newton. BFGS is the acronym of the authors. It was invented in the 70s. It's a standard deterministic algorithm. So CMES, it's a stochastic algorithm. I will go back. I will talk a bit more about later on, right? But this is my representative of a stochastic algorithm, and this is to illustrate this robustness to noise, and I have data to illustrate this.
And the Hessian estimate in the BFGS, do you again use the zeroth order estimate of it?
Yes, exactly. So I didn't copy the update. I didn't copy the update of the BT in BFGS, but this is an update that involves the gradient. And there we use it in a derivative-free mode, which means that we do a finite difference estimate. I mean, it's when...
So you replace the Hessian estimator with the gradients with the zeroth order gradient estimator.
So I replace, so if you check BFGS, so the BT update, it's an estimate of the Hessian, which is iterative. And this estimate, if you see the formula, it involves the gradient. And I'm saying in this update formula, which was invented in the 70s, I just take the gradient. For the gradient, I take the finite differences, right? But I don't do, I don't estimate the Hessian by doing finite differences, right? I just take the algorithm how it was and just plug the gradient instead of the gradient. I plug finite difference estimate of the gradient, and this is actually how it's implemented. So I use the implementation of SciPy optimize. And this is how it's implemented, and this is how, if you use it in a derivative-free mode, this is the algorithm you are using. Okay, so, right, so here, this is a SciPy optimized implementation of BFGS.
Yeah. And when you make a finite difference, when you build the difference, each function evaluation comes with its own noise.
So, yes.
Yeah, okay. So
yeah.
When you build the difference, you add up two Cauchy noises.
Yes. You don't have always Cauchy noise, right? You have with a certain quality. Okay. Thanks for the questions. Right. So now this is this is the motivation for why stochastic algorithm. Now I said in the introduction that in the discussion with Sean Main, he was surprised that we could get fast convergence for some stochastic algorithm. And actually, the fast convergence is for this CMAS algorithm that I will give the details later on. And the reason why is because if we think about stochastic optimization or stochastic, stochastic approximation algorithm, so probably many of you have in mind the roots of stochastic optimization or stochastic approximation algorithm by Robbins-Monroe and Kiefer-Wolfowitz, where the idea is, so it's typically in this noise setting where you optimize the expectation of a function, expectation with respect to the noise. So the way the algorithm works, so here I just give the Kiefer-Wolfowitz, which is a derivative-free version of Robbins-Monroe. So it's a stochastic approximation algorithm, and the way you estimate the optimum of the problem, theta t, so again, theta t is a vector of R to the n, is by doing this update. So here we have in the noise setting, right? So we have xi and xi t1 and xi t2 that are instantiation of the noise, and you make finite difference estimate of the gradient. So ei is a coordinate I of your is a vector I of the canonical basis, and this is finite difference estimate with a step size delta t. And this estimates the gradient of f with respect to the first variable at a given xi that you instantiate with to noise instantiation. And what is typical in this setting, Kiefer-Wolfowitz, and a variant of Kiefer-Wolfowitz, is to take AT and delta t that are deterministic, predefined sequences. And it's also classical that it's possible to prove the convergence of Kiefer-Wolfowitz algorithm under the condition that those predefined sequences, they have to converge to zero, but not too fast. This is what we have here. This series diverges, and this tells me that it converges to zero. And then theta t converges to the minimum of f. So there are some assumptions that I don't detail. Basically, some are, you need some regularity on capital F. But basically, it converges to x star at a rate of O of 1 over t to the 1/3. So sorry for the typo here. It's t to the 1/3. And those were already early results, right, in the 50s, 70s that were proving this. There are variants of this Kiefer-Wolfowitz, in particular one algorithm is called FDSA for simultaneous perturbation, where the idea was to make a more effective gradient estimate, where instead of using 2n function evaluation, it's basically 2 function evaluations. This was invented by Spall, and the convergence results, they are also similar. And what I want to emphasize is typically this condition here of predefined sequence of step size that converge to 0 not too fast. Right, so now what I will show in the second part is that it's actually possible to converge much faster than this O of 1 of t to the 1/3. And actually you can get geometric convergence for some stochastic algorithm in the noise-free setting. So geometric convergence is also called in optimization linear convergence. And to a smaller extent, this is ongoing result. I mean, result we are currently finishing to publish in a noise setting. I will explain which noise setting we can also get this geometric convergence. And we do this while getting rid of those deterministic prefix step sizes. So if you do optimization, practical optimization, in practice you are not happy with predefined sequences of step sizes, because it's quite intuitive that this is not optimal, right? If you start far away from the optimum, the step size needs to be larger, and if you take the predefined sequences of step size, this is not taken into account. I mean, this is known. I mean, when you use in machine learning stochastic gradient, you typically don't use anymore these predefined step sizes. This is a paper already by 2013, and I think there were already some before, was proposing to change those Pesky learning rates. Right? So now I promise this geometric convergence, getting rid of this deterministic prefix sequence, also without using line search. And I also promise that I will get rid of function value in the update. And I want to say it's not a joke, so it's 1st of April, but it's not a joke that I will show some algorithm where we don't use f value to still optimize the function, right? So it looks weird, and wait for a few minutes how we can do this, right? And I say it's not a joke, okay? So that's the program now. I present another class of stochastic algorithm where we get geometric convergence. We can prove the geometric convergence without predefined step sizes and without function value. Okay, so let's see how we do this. So now we are in context of stochastic algorithm, but now the stochastic part of the algorithm is used mostly to sample solution in the search space. And what we do is that we encode in the state of the algorithm which will be adapted. So we encode the parameter of the probability distribution. And if you can guess on the right that this probability distribution is Gaussian, here I display the level set of a Gaussian distribution. You might know that CT, the coherence matrix, parameterize the lines of equal density with which we sample. The sigma t will be the scaling of with which I sample. And basically, this is the first step in this class of algorithm. Given state of the algorithm theta t, so with mean mt, a vector of r to the n, step size sigma t, coherence matrix ct, I sample lambda candidate solution. Then I optimize, so I need to evaluate them on f. So I evaluate them on f. I rank the solution, and if I have a noisy function, I rank them, but I have here some noise. And now this is where my point of not using function value comes from. So I use it to rank the solution from the best to the worst, I minimize. But in the update of theta t, I don't use the function value, but I only use the permutation which contains the ranking of the solution. So the update, I formalize in abstract way as a capital G, and I will give an example of the G update. But the point is that the update only relies on the ranked vector u here, and not on the function value, right? And this is where I say I don't use function value. So I do use it, but only to extract the permutation of the candidate solution. That's where I was saying it's not a joke, right? Of course, this update G should drive MT toward the optimum, and let's see how this can do that. So now you can ask yourself, why the hell do you do this ranking instead of using function value, which is more information? And the reason is, again, robustness, because if I do this, if I optimize now a function f, or I optimize G compose f, where G is just a strictly increasing function, then I get the same ranking. So I will extract the same permutation S, and therefore I will get here in theta, I will get the same update, which means I will get the same convergence rate. And this is pretty cool feature now, because if I look at those functions, so here I look at the x-axis is x, f of x, so this is the easiest function possible, nicely convex. And now I just took g1, which is strictly increasing, and g2 strictly increasing. They look much harder to optimize, but with this class of algorithm that just use comparison and not function value, I will get the same convergence rate, right? So I gain in robustness by doing this. All right, so now this abstract class of algorithm, they capture some algorithms that were called in evolution strategies. So they were invented in the 70s, inspired from biology, and it's rather in a computer science setting. So the inventors were Ingo Reichenberg and Paul Schwefel. And among this class, the CMAES, so I've shown performance of an algorithm CMAES. So CMAES is the most refined from the class. So it was invented, first paper is 2001, and there were refinement of the main algorithm till 2006. And this algorithm that has quite a lot of impact. So we see for 2 years now an increase in the number of downloads of the two main Python code of this algorithm, like I think it's more, even more than 70 million today. And the joke is, I mean, the inventor there are Andreas Ostermeier and Nico Hansen. So Nico Hansen is also a researcher at the CMAP at INRIA also. He was doing his PhD with Ingo Reichenberg, and the funny thing is Ingo Reichenberg, who is one of the father of evolution strategies, never liked CMAES because he said it's not and not bio-inspired. And till the end of his life, I think I talked to him three years ago, and he still told me, no, I don't like CMA, it's not enough bio-inspired. So it's just to say that it comes from biology, but it's not too much bio-inspired now. And the point I want to make is the designer, when they invented this algorithm, Andreas Ostermeier and Nico Hansen, they care about having an efficient algorithm on wide classes of function. They care about having a parameterless algorithm. So there are a few constants that I will highlight. They are just properly tuned, and not it's not the user that has to tune them. And they didn't care about having a convergence proof, which made the life of the people who try to prove the convergence kind of hard. And in a sense, we can say it's successful, because if the framework for designing the algorithm was restricted by the framework to prove convergence, they would have never come up with such an algorithm. And as I said, it made the life of people who try to prove convergence difficult, and in particular, it required to develop quite a lot of new mathematical tools to arrive to the convergence, to prove the convergence of CMAES. All right, so now let me give some update, right? I was very secretive about update. I didn't say how the step size sigma t and how the mean are updated. So let me give you a bit of intuition or idea of how it's done. So we have those two steps, right? I said earlier, the first step is to sample candidate solution according to multivariate normal distribution, to rank the solution and to extract the permutation. And now we have to update 3 parameters. So the mean vector, so the mean converges to the optimum. So the mean, it's not too difficult to think, okay, the best you can do is just make a weighted average of the mu best solution. So mu is typically lambda half. So you move the mean towards the best solution you observe. So the step size, so here I simplify a little bit, and we explain the full algorithm afterwards. So the step size basically, so what you do is you track if the mean shift is larger than what you would have under random selection, in which case you increase the step size and otherwise you decrease. So this is what is implemented here. And then we have a covariance matrix. So covariance matrix, there are 2 updates. So, but basically you make this outer product of those vectors here that are depicted. So it's candidate solution minus the mean. And as I said, it's not the full algorithm. So the full algorithm has 2 additional parameters. So those are some vectors, P, T sigma, PT plus 1 C. There are 2 vectors to speed up the adaptation of the covariance matrix on the one hand here. So you add in addition a rank 1 update along this vector, which is basically the path followed by the algorithm. And you also use this cumulation here to update the step size. So I don't want to enter into details, but those are 2 mechanisms that were carefully designed and tuned to speed up the adaptation of the covariance matrix and of the step size. Right, so that's the CMAS. So it answers your question, what is CMAS? So this is this adaptive algorithm where the parameter of probability distribution are adapted. And now what speed of convergence do we get? So if we take the simplest function possible, or okay, sphere or convex quadratic function, we want to see what's going on. So here, this is here for a given Hessian. Because the algorithm is invariant to modulic transformation, this will hold for any G where G is increasing. And what we observe is linear convergence. So linear convergence, basically, here we display the function value in black in a log scale in terms of number of function evaluation. And what we observe is that after a while, then we get this linear decrease in the sense that the log of the distance to the optimum converges to minus infinity, like minus a constant, right? Minus CR here is the slope, times the number of function evaluation. And the nice thing is that the algorithm, covariance matrix, become proportional to the inverse Hessian. And this we can see if we check the eigenvalue of the covariance matrix. We see a first phase where the algorithm learns gradually the proper eigenvalue of the Hessian. And then here in this stage, the algorithm is stable in the sense that the covariance matrix, the ratio between the eigenvalue doesn't change. And the matrix still converges to 0, but in a way that is proportional to the inverse Hessian. So there I show linear convergence on a convex quadratic function, but actually this linear convergence we observe on wider class of function. Go ahead. Yeah.
Can you show the algorithm again?
Yeah.
So here, so all the parameters, like whatever you have here, everything is, where do you start? What is the starting point? How do you start?
How do I initialize, you mean, the algorithm?
How do you initialize?
Yeah. So I initialize, the state parameter are initial mean, initial step size, initial covariance matrix. So, and I have a lambda population size, which is tuned by default. And that's all. So I provide initial mean, which is my initial guess to the optimum. Initial step size. And initial covariance matrix, typically you put identity because you have assumed that you have make all dimension of your problem, all coordinate kind of with the same scaling. So that's all what I do. I initialize and I let the algorithm go, run.
And what is CC, C
yeah.
sigma,
okay.
WIs?
Yeah. Okay, so thanks for the question. So those are indeed parameters, but they are pre-tuned. And the user should not change it. So it's very sensible to that, but I mean, there was a careful and hours of tuning of those parameters. So I can say, so all what is in purple are hyperparameter, fixed hyperparameter to the algorithm. So typically, WI are some weights. So they are positive weights and they decrease. So you put more weight to the first candidate solution and so on and so forth. And we have some theory to know what are optimal weights. So this we know how to get fast, how to get optimal weights to get fast convergence. And for the learning rate, C sigma, D sigma, and C mu, there is less theory, but there is a careful tuning and careful numerical understanding on how to tune them. And this was done. Basically, if you take them too large, so they are between 0 and 1. If you take them too large, it doesn't work. And if you take them too small, it's too slow. And then you make this trade-off on a few test problems, and they are carefully chosen, and they are with a scaling with the dimension. But basically, the user doesn't tune this. Yeah.
So I understand that WIs are sort of related to the ordering, and it might depend on lambda. And how do you choose lambda?
So lambda, there is a default setting, which is on the order of log of dimension. But this you can choose. Basically, what we observe is if you want it to be more robust to local optima and to noise, you should increase lambda. But basically, it can be the order of the dimension. But I mean, basically, it works for all lambda larger than 3. And the more rugged your function is, the larger lambda should be. But it also works for smaller lambda. But this is typically the only thing that the user might try, to increase lambda if it sees that it converges to local optimum.
Okay, so you say that roughly it should be of order of the dimension.
But by default, if you don't do anything, it will be log of n. And I discussed with Nico, considered to change the default to, I think, something order of dimension now.
Okay. And this parameter C mu C1, sorry for too many questions and you can interrupt me. But C mu C1, they should somehow depend on regularity of the function, right? Some sort of, I don't want to say smoothness because you avoid it in every way possible, but something like that.
I mean, no. I mean, they are not. You don't tune them to the function, right? They are tuned, and you don't adapt them depending on the function. It's just they are tuned. Basically, the way it's tuned, you know that you make some simulation, and you know that, as I said, if it's a bit too large, it just the algorithm is not stable anymore, and if it's too small, it is stable but extremely slow, and you make this trade-off. And I think it's basically tuned on 2 or 3 functions. And that's it for then using it on any function. Okay, so yes, so I said we have this linear convergence on wide classes of function, and this convex quadratic illustrates the learning also of second order information. And now the question is, can we prove this linear or geometric convergence? And the answer is yes. And I will explain quickly. How long do I have?
15 minutes.
15? Okay. So I explained the main idea. So first, we started, of course, with analyzing not the full CMA. I mean, this looks like a very complex algorithm. So what we started to analyze is just step size adaptation, step size adaptive, so which means that the covariance matrix is frozen to the identity. We don't have those commutation parameters, so we only adapt the step size, and we don't even adapt it using additional accumulation because it's also much more complex to analyze. But let me explain the idea, because they turn out to generalize also for analyzing CMA. So we want to prove this linear convergence, which means that we want to prove that the log of the distance to the optimum divided by t converges to the constant minus constant. So without Loftus generality, we can assume that the optimum is in 0, and I assume only a step size adaptive algorithm. And I write down the step size update is multiplicative, and I write eta star, this random variable which contains the step size update. So we want to prove, therefore, that the log of norm of mt divided by norm of m0 divided by t converges to minus a constant. So this, I use the property of the log. I write as the sum of log of mk plus 1 over mk in norm. And here I would like to use a law of large number to take the limit for t to infinity and say that this converges to the expectation of this quantity. So we cannot use law of large number for independent variables because they are not independent. So the trick we use now is that we artificially introduce sigma k here, which is a step size. So I introduce it on top below. I use the formulation of the step size at iteration k plus 1 with the multiplicative update. And then I find that what I want to get the convergence of, I can write as a log of this quantity, norm of mk plus 1 divided by sigma k plus 1. I have the same quantity but 1 over, and I have this here step size change. And now it turns out that if I introduce zk, which is mk over sigma k, I can express what I want to study the convergence of in terms of zk. And let's assume for the moment that this is a Markov chain. Then I can use some result on Markov chain, in particular some results that are in the main 3D book, that tells us that if this chain here is stable enough, then this converges to the expectation of this term with respect to the stationary measure of the Markov chain. So in case, if I'm able to prove that it has a stationary measure, then I can conclude that the algorithm converges. And we see that this term and this term will cancel. So in the end, I will have that the convergence rate is just the expectation with respect to the stationary measure of the Markov chain of the log of the step size change. And this is what defines the convergence rate, right? So that's the idea of the proof. Now, of course, I said let's assume that ZK is the Markov chain, and let's assume it is stable. So now this is basically what I need to prove to show the convergence of this class of algorithm. So we can ask ourselves, on which class of function do I have that this quantity, which is the normalized process, is a Markov chain? And the answer is basically on this class of function. So if the function is so-called scaling invariant, and scaling invariant, we can think about having a function with a level set which is scaled. So the level set doesn't need to be smooth. It can be here and smooth. And here it can also give sub-level set that are not convex. And so on this class of function now, it's not too difficult to prove that the class of algorithm I was talking about is such that this MK is a Markov chain. So this is the easy part. And now the more difficult part is to prove, I'll go back here, is to prove that on this class of function, the chain ZK is stable enough. And so this is a hard part that we have to do for each new algorithm we want to analyze. But the good news is that this is still possible, right? We can rely on result on Markov chain theory. So basically, we have to prove some stability result related to irreducibility of the chain, Harris recurrence, positivity. And then this is a theorem we find in the main treaty, where if we have those stability properties, then the chain is ergodic. We have invariant probability measure, and we can use a law of large number, which concludes the proof. So now, on which class of algorithm, on which condition did we manage to prove that this Markov chain is stable? So basically, we did that for a few algorithms. So I have to mention that basically the tool we are using to prove the stability are Foster-Lyapunov drift condition, which basically we need to find the right potential function so that outside the compact, a small set outside the compact, we have this drift condition that holds. That tells me that the chain goes back inside the search domain. And this we managed to prove for a few algorithms over the time. And basically, this is for step size algorithm, this is here the assumption we have on the level set. So we managed to prove for step size algorithm, we still need smoothness of the level set. So basically, we exclude this type of functions. But we managed to prove it provided the level set is C1. And we can actually make the assumption a little bit weaker. All right, so this was with some work we did in the past with some PhD students. And the news now, I mean, this will be my last slide, that we can actually generalize this to prove the convergence of CMAES. This was the PhD thesis of Armand Gisler, who defended at the end in December 2024. You can imagine that this is much more complex. The Markov chain is much more complex, and we needed to extend quite a lot of tools to do that. But this is possible, and this is what Sean Main was actually a reviewer of the thesis of Armand, and this is how he got to know about those results. And the other news, because I started with noise, the other news is that we can, to a certain extent, also get this geometric convergence or linear convergence when we have multiplicative noise. So it's not additive noise, because in additive noise we would lose this linear convergence. But if we have additive noise, and if we introduce a small bias towards increase for the step size, which is also something which is reasonable in practice, then we can also show that this adaptive ES algorithm do converge linearly. And then I will stop here. I'm happy to answer questions. And this is all the acknowledgement to my colleagues who contributed to this presentation.
Almost on time.
Almost.
Okay. So we've got time for questions. If there are more questions.
Thanks all for the presentation. I was wondering about the Oracle model. Like, are you saying that if I replace the zero-order black box by pairwise comparisons, because I feel like at the beginning you said like you can replace this black box by pairwise comparisons, but then you have some properties of the level sets of the function. And yeah, so this goes to my also second part of the question. Your assumption on C1 of the level sets, is it C1 of the level set of the original function, or that there should exist a monotone transformation that makes it C1?
No, it's no. They should exist a monotone transformation that makes it C1. No, it's not the original function. It's really the level set. So you can overall the convergence result holds for non-C1 function because you can always make the function non-C1 with G. Yes. So I think we have to exclude this type of function where you have a kink on the level set. And actually we don't think that on this class of function we don't get it, right, practically also. And so it's reasonable to exclude it from the proof. Yes, but otherwise, yes, the function can be discontinuous with this G trick, but the level set itself needs to be smooth.
And so all your results hold in this Oracle model of pairwise comparison.
Yes. Yes.
Function value, you don't care.
Yes.
At all.
Yeah. Okay. I mean, there are some work analyzing complexity, right, in this comparison-based setting, or I mean, some people call it rank-based or comparison-based. There might be even a third name. Yeah. Okay. Yeah.
I might ask another question. So, do you assume that your function is unimodal?
Yes. Yeah. This holds for unimodal function. Yeah. Yeah, I should have said that. Yeah. I mean, this is so it's yes. The assumption I was a bit too quick. So it's scaling invariant, and yes, we need unimodal with respect to scaling invariant with respect to a point, and yes, unimodal.
And since lambda does not appear in the convergence rate that you showed, at least on the slide, if I'm not mistaken, then I assume that if you increase the number of lambdas, right, the number of samples, if you do like exponential in like, I don't know, 2 to the power of d times sampling, you just measure every possible direction, then you should basically recover the best rate and you should converge very quickly, right? Regardless, I mean, it should kind of affect the convergence quality. Like if you take too many samples, then you have too much information about the function. Basically, you just brute force the solution.
Yes.
Then you should converge, given that you can do this thing in O1, which you can't. But if you can do it, then you can converge very quickly, right? Do you see this type of effect? So
first of all, to be fair, the convergence rate has to be divided by lambda, right? So here, I mean, when we compare performance, we compare in terms of number function evaluation. So here I write it, I don't divide by lambda, but I should kind of divide by lambda. And it's also not because it doesn't appear. It is there, right? The convergence rate is not always the same. I mean, I could put a dependency in lambda in this convergence rate, right? So, of course, there is a trade-off. If we plot this convergence rate divided by lambda over lambda, there is a maximal convergence rate that I expect on unimodal function to be pretty low. Yes. But of course, I mean, right, if you don't divide by lambda and if you do infinitely samples, of course, this is optimal, but this is not very good in practice, right?
Of course. No, yeah. I just wanted to see if in your results you can see the effect of taking large lambda, like quantitatively, basically.
So yeah, so we don't, I mean, when I want a quantitative convergence rate, I simulate it, right? The theory doesn't tell me much quantitatively because basically the convergence rate depends on the stationary distribution, and I typically show the existence, but I don't say, I cannot show too much besides it exists, and I also need to show integrability because with integrability of this, so it's already tricky enough to just show those properties. So I don't get anything quantitative on the convergence rate. And what Armand showed also, we can have the sign, which is not completely trivial in the first place, also to get the sign. But we don't get something, theoretically, we don't get something quantitative. There might be other technique that allows to bound, but not with this approach. But otherwise, okay, from simulation, we know quite a lot about the convergence rate on different functions. Yeah.
I can ask another question if you have time.
Yes,
or we can do it after.
Or we can do, I don't know, with your stomach, but mine is.
Okay.
We can thank again.